Alright, hell yeah. So this video is going to be looking at integration from a fundamental perspective, where if you can read something, mathematically it should make sense. And so one of the simple things that we can do for differentiation and integration is change this dx to a delta x. Delta x represents some sort of change, like a tangible change. You know what I mean? Sometimes for a lot of physics problems, if this is like, if my variable x is time, and that's usually represented with a t, and then you have a dt, that's going to be a change in time. I like to throw in 1 second, you know what I mean? And that's a pretty big, that could be a pretty big quantity for some physics problems. But at least it gets you the notion that this integral, you are multiplying by something. You're taking, and then even breaking down to the fundamentals of, like, hey, this part right here. Now this part right here is called the integrand, but it is a function, and it's usually represented with the lowercase f of x. And when we do take the integral, we get the uppercase f of x. Both of those are functions, and it was just this month of like relearning what a function is. Hey, like a function is just going to output one single value. So a function has a variable, and and it can have multiple variables, but just the simplest function will just be it'll have one variable, like x, e to the x. That's a function, and we can put in an x value of negative infinity all the way up to positive infinity. It's a function because it outputs only one value. And so if you plotted it, it can go up and down as much as it wants. It just can't overlap like this, where you get, that would be the definition of a function. But anyway, that said, this is still also just a value. So if I did put in a value of x, if I chose x to be something like 1, I get a number for this. I get e to the 1. Let's say that's 2.7. Sweet. And so that value now represents something. And so even though these are mathematical expressions, like my question is like, well, I'm going to be using integration, differentiation, and calculus for physics problems, and physics problems have dimensions. And so in this integral e to the x, and also integral of sine of x or integral of cosine x confused me, because I think the simplest integral to do is just integral of x, you know what I mean? And then it becomes the power rule, where you get x to the 1 plus 1 divided by 1 plus 1. So you're going to get 1/2 x squared. So integration of x. And so if this was the integration of x, it would be the integration of x dx. And you would literally have, and that could be something where you could have units, very tangible units, on what x represents, and then you're going to multiply by a change in x, and so you just kind of doubled whatever units you had. If you had the integration of x, and x was in meters, and then you took that value in meters and then multiplied it by a change in x, well, now your units are meters squared. And so this one in particular, and sine of x and cosine of x, are dimensionless. And this is one of those mathematical statements that, I don't know, I've never even formally been told that if you have, if your variable is a power and it's supposed to be representing something physical, it has to be dimensionless. Because this comes up all the time in physics, where you have e to other variables upstairs in this exponent, and I had no idea that they have to be dimensionless. Just because if you had e to the meters upstairs, and then, like, let's say you had e to the x, I can't even fathom why, like, I don't know if the meters would square or what, but I'm just going to leave it at that. Okay, hell yeah. So now let's see what I have here. Can a dimensionless function only have a dependent variable that is also dimensionless? No, so this was kind of interesting, because if I'm starting here, and it's just like, does this have to, if this is representing something dimensionless, does this value have to be dimensionless? And I don't even know where I want to start with the Google. Probably somewhere I'm not going to lose my mind. What are the units? Yeah, so this was like, I was just like, well, what are the units? And let's go back to this integration. Because if we are integrating this, the thing about integration is that we're going to get a function. And once we get that function, we know that if we take the derivative of it, we return this function. And that's what I'm most practicing this week and this month when it comes to integration, is looking at it like there's no just one forward process to take an integral and do an integral. It's kind of like a backwards process. And one way that I like to look at it is if you have like the square root of 25. I just want to throw that up there. But if you have the square root of 25, there's no forward process to get the answer of 5. There's not, an equation where you're just like, okay, I'm going to multiply something, divide something, subtract, and add, and do this in a step-by-step process. It's more of a guess and check. You know what I mean? So to do the square root of 25, you need to say what times what equals 25. And so that's kind of more explorative. And that's what we need to do with integration. It's what over here, what is this equal to? What function, where if we took the derivative of that function, we would return this part. And for e to the x, if I had e to the x over here and I took the derivative of e to the x, I get e to the x. And that's where it's just like, okay, so if I have a function that's e to the x and I take the derivative of it, like those two functions should have drastically different units. Because let's say I do have e to the x, and what does the derivative say? And so that's what we have right here. The derivative of e to the x with respect to x is I'm going to change whatever value this is and whatever dimension it has, and then I'm going to divide it by the change in the variable that I'm changing. And with a function, your input can have a dimension, and then your output can also have a dimension. We've already talked about how this is e to the variable, or a power to a variable, so it's, for physical sense, it's dimensionless. And if we have the change in something dimensionless, so x has to be dimensionless. And so e to the dimensionless, a power to the dimensionless, this is dimensionless, and we've already said that x is dimensionless. So this derivative, we're changing this function with respect to the variable, but it's a change in something dimensionless divided by a change in something dimensionless. So our result is something dimensionless. So the integrand of this is dimensionless. The integration of it is also dimensionless. Now this could represent something in physics where you do have a dimension. How would that be? Well, maybe this whole thing represents, I'd have to do that for another video, but it seems like you could have a constant out here that's not part of the equation, because any constants can fall outside of the integral. And so they're not, any constants would fall outside the integral and would be there at the start and finish of the integration process. So if this was the derivative, now does that even make sense? Let's say we started with the derivative of e to the x divided by dx, and we have a constant here that's 2, and it's 2 apples, or whatever. And maybe we could represent that as k. If k represents, and we could input 2 apples, but k represents the unit of apples, when we take a derivative, one of the rules of derivatives is we can bring that constant outside the derivative, the actual thing that's changing. So the units can come outside. So therefore, we still left with this dimensionless numerator divided by denominator. And I really do. You need to think of this as a tangible fraction. And you can do that if you change the d to a delta sign. We're going to change x by a very small amount. And, I mean, you don't even have to change it by that crazy of amount. Like just whatever, you know, three to four orders of magnitude of 10 less than, you know what I mean, your problem, that's usually good enough. If it's with time, if you go time to 1,000th of a second, holy tool, that's plenty. You'll be accurate enough. And then you can change you know, so if you change your function e to the 1 and then e to the 1.001, that's going to be a change in this value. And you know that this changed by just 0.001. So you should always be able to just tangibly talk your way through putting a delta here. And yeah. So hell yeah. So if the constant was outside of the derivative, the units on that wouldn't change anyway. And so let's say this was our capital F of x. We're going to take the derivative of it, and then we're going to get this value plus multiplied by the constant, and the constant would still have those units. So yeah, so that's where from physics, because I was just like, well, how do you have the integration of sine of x, cosine of x when they're dimensionless anyway? You know, if you have the integration of sine x, you're going to start with the negative cosine x. And I can do that one in my head because I'm thinking of the graphs. What I did there was if I'm taking the integration of sine x, you know, I know it's going to be the cosine because sines and cosines, but do I know it's going to be positive or negative? Well, once I got that capital F function, I'm going to take the derivative of it. So let's say I just struck out and chose cosine. I'm going to see that the cosine function starts at 1 and goes down, you know, at a 45-degree angle, but it starts at 1 and then goes down like that. And so the slope of it's 0, 0, negative 1. And so and it's always negative. So the derivative of cosine is always going to be negative sine. I started with sine. I didn't start with negative sine. So therefore, the integration of sine x is just the negative of cosine. So that it would start down here at negative 1 and then have a positive slope at a 45 up to a 0. So negative 1 to 0. So that's what I'm doing in my head there. But both of those, sine and cosine, the integration of them, they come up in physics all the time, especially with like curved ramps and stuff for gravitational physics. And sine and cosines are percentages of kind of a quantity that you're working with. So that quantity, again, could be like this constant outside. It could be gravity. You know, we're trying to figure out the force of gravity along an inclined ramp, and the angle changes. And so you're going to have some sort of angle change, sine of the angle. You're going to, the sine of the angle is going to be the percentage of those vectors that are now driving the force, you know, and changing velocities. It could be a change in work. It could be a change in velocity. But still, sine and cosine are dimensionless, but they represent a percentage of whatever constant was outside. So, and I think, like, stuff like this is no one talks about, and that's why I just turned on the camera, just because I was just like, hey, we need to do this. And even though it's kind of rough and tumble. But hell yeah. So we're going to kind of end with whatever I had over here. So from a mathematical perspective, this is where they talk about how it's problematic to have e to the x where x has a dimension like length, because the exponent of a mathematical function must be dimensionless. The exponent of any mathematical function must be dimensionless. I don't know exactly why. I haven't played around with that. See, I'm of the mind where it's just like I don't trust, you know, I mean, I trust things to a degree, but it's just like I'm not going to understand or know things, and you know, it's like someone telling a really good story and then you just forgot all the details. You're not going to tell that story to another person, even though you got the gist that it was a pretty good story. Hell yeah. So this is a fundamental rule of dimensional analysis, and raising a quantity with a unit to a power would result in a physically meaningless quantity that is neither a length nor a dimensionless number. For the expression to make any sense, a physical variable in the exponent must be made dimensionless first. So that's what I'm going to be, and that's kind of cool, because now when you see an equation for kind of complex physics stuff, you can be like, oh, hell yeah, it's e to some sort of variable of t. Well, there's got to be constants in there that make that variable of time dimensionless, and that's what we see. Cool. So radioactive decay. This is e to the negative lambda t, and then I looked up, hey, where did I look that up? I didn't. I mean, I did, but then I probably closed that one down. Anyway, yeah, so that lambda is going to be units of inverse time. Okay, and then I was just like, well, because the most important thing about this integration, I'm going to go to here next, is that you're multiplying by this. And this is the first time I've ever gone over this stuff, and that's why I really like the Google AI, because if you have a math question and you know how to frame it, you'll get pretty decent answers. Like, what is this called? This whole thing, what is the whole thing called? And does it have parts? And what are the parts called? Because I was looking up the term integrand, and integrand was, well, what they said is that if you have the integral, the differentiating the integral with respect to the variable will give you the integrand. But if you take the integration, the integral, and you differentiate it, you're just going to get this part. You're not going to get the dx part. And so I was curious about that. And so yeah, so this part is just called the integrand. And then this is your differential. I did not know that. And this is where I'm okay now with learning terminology, because especially with like AI, because you can ask a question and get an answer and everyone can be on the same page. I think 20 years ago you didn't have this. You just learn from your teacher and you're just, yeah, I kind of know it. It's going to be a tool I'm going to use. I have no idea how to even pronounce anything, but I know how to use the tool. Or maybe I don't. Maybe I'm actually, there's going to be times where I strike out using this mathematical tool. All right, hell yeah. So yes, this is called the differential. And my game on differential calculus, if I do have a function, I'm going to take the derivative. I know that I can only, if I'm going to do that, if I'm going to do the little fraction, the little Leibniz, and that's where I don't like the video. There's one circulating the internet that's just like, that's not a fraction. Well, yes, it is, as long as you take dx to represent a delta of your variable, and then the upstairs is going to be a delta of the function. Those are real things, and a function generates one value, and a change in that variable is going to generate one value. And then so you have a fraction of one value divided by one value. You just get to choose the value, and then that's the most important part about in differential calculus, is if I set that up like, a function, d of the function, d of f of x divided by dx, or with respect to x, I can only take, I can only set that fraction up like one variable at a time. Or maybe it only makes meaningful sense to set that up one variable at a time. Oh, and that's interesting. If I had f of xy and then did a fraction dx and then dy downstairs, I think that would also make sense. That, oh yeah, that makes sense. You just have to do one first and then the other one second. So I'll make a video on that. But it's only if you actually look at these things as mathematical expressions that we're all familiar with, does the story, set in. That it's not just some sort of hocus pocus, that this thing goes to such a tiny number that now we just, lose grasp of what it actually is, and then just go to tables and lose fundamental concepts of what's going on. So yes, if we take a double integral, I can take a function that has two variables, f of x and y, and I can differentiate with respect to x, and I can and then I'll have another dy. So it's going to be a multiplication, where if I took the derivative of two variables, I'm going to have those stacked in the opposite way. And that's kind of fascinating. I'll have to explore the derivative, because that gets into partial derivatives and stuff like that. But I think it's good to know that you can only do one thing at a time. Even if you're taking a partial derivative, you're not going to take the partial of this function with respect to x and then downstairs also with respect to y. That's the opposite of what even the partial derivative, it's just like you're going to set everything else constant, but for now, and that's what When you take the integral, they call it iteration even, where if this is a double integral, this is y e to the x dx dy. When you take the integral with respect to x, you're treating y as a constant. It can come outside the integration for now. You're putting the dx dy to the side, and you're just doing the integral of the inner part, getting a value, and then you're taking the second integral, that double integral. And so, hell yeah. All right, so that was halfway well said. Oh yeah. So we were just going over what are these called, and when you're doing integration, you have to choose what variable, what's your differential. Sometimes you'll have e to the x, and you're actually treating this as a constant because you want to know, this with respect to time. That happens a lot. I don't know. You're just like, cool, I have this, but actually, like, I just want to know how this changes with respect to time, and there is no time value, and so it's all a constant. So yeah, so this is interesting. But yes, you have to choose this differential. I don't know, I was just saying, is the dx multiplied by the integrand the most important part of taking an integral? And that kind of... It's not the most, it's a crucial part because it specifies what variable you're going to be integrating with. And so once you do get that function, that is the variable you'd take the derivative to. And so just like the square root of 25 doesn't have a one-way process, it's like what times what is 25? That's a backwards process kind of. It's like 5 times 5 is 25. Cool. That kind of set up that process. When you take the integral with respect to dx, you're getting a function, but you have to double check that function by taking the derivative of it to return the original function. Hell yeah. Yep, and so this is the integral sign. The whole thing is called the integral or the integral expression. This is the integral sign. The three parts are you have the integrand, that's the function, where if you did get the capital F after taking the derivative, and the capital F can always be and is associated with the capital F plus C, because when you take the derivative of it, the derivative of a constant goes to 0 and you're just left with f of x. And that's why that's the bummer about integrals. It's like confusing because it's not just one function, it's a function that has a specific shape, but then you can have it anywhere along the y-axis you want. And so it's the family of functions. It's an infinite family of functions just shifted, along the y-axis wherever. Yep. And until you actually do a physics problem, and kind of set a location, and that's using your initial conditions. Sometimes final conditions, sometimes a midpoint condition, but some place where that function is going to go through something like a physical tangible location. And then the differential, this is dx. This indicates the variable with respect to the integration is performed. For example, dx means you're integrating with respect to that variable x. Hell yeah. And I'm just trying to get better at just like talking my way through this stuff. So that's pretty sweet. In an integral, would you say I'm integrating with respect to x if dx is the differential? Yes. Just ask Google Edge, like stupidly easy questions that you think. All right, hell yeah. In multivariable calculus, can a single integral or differential equation only be taken with one variable at a time? And then this is where no, and I'm kind of getting that. Yes, like you can do a triple integral. You can differentiate with respect to both x and y, but you do so in steps. And each step you can only do one thing at a time, and that's where. But there might be other methods where you do things kind of all at once. But partial derivatives, if you look at them, it's a partial of the function with respect to x, and then plus a partial of the function with respect to y. And then we just talked about the iterated integration approach, where you start with one variable, pick a differential dx, and if there is a y, you're going to treat that as a constant. Get that value, and then move on to the integration of your where your differential is the dy part. Anything with y's get integrated. Hell yeah. So if you have a function f, x, and of two variables, x and y, like x x times y. What is the integral? Well, you're going to do a double integral. And so here they just said, even though they have one integral sign, they're doing this with respect to x first, getting a value, and then taking another integral with respect to y. So typically this would be written as just a double integral right here, xy dx dy. But they're showing it just as in steps, and that can be kind of useful too, maybe. The y pops out. X dx, the integral of that is 1/2 x squared. Hell yeah, plus a constant. You had a y outside. The y gets multiplied by both the constant and this x squared, 1/2 x squared. So now we're going to take the second integral with respect to dy. This has a y in it, so that's going to be 1/2 c1 y squared. So that's what we should see for... oh man, yeah, there we go. Oh, I don't like that. When we integrate this with respect to y, this becomes y squared divided by 2. So that's x squared y to the 4, x squared y squared divided by 4. So that's what we have right here. And then we have c1y. When we differentiate this with respect to y, we get, yeah, I don't know what they're doing with that part. See this. I got that part. This second part becomes C2 with respect to x. I don't see that. C this constant is xy. All right. C2 of x. I don't get that at all. But anyway, hell yeah. All right, we're probably going to be ending it there on a low note. But yeah, that's the crazy thing about math is just like, yeah, you get somewhere where you're just like, ooh, I don't even see what they're doing. And I could ruminate on that for like an hour before and still not know what the hell they're doing. All right, but hell yeah, that's going to be a video. Thanks for joining me. Booyah.